Namaste. Welcome to the lecture series on the subject Basic Thermodynamics. This is module 3. In that part 1, the second law of thermodynamics. So lecture number 1. Myself Dr. Satheesh Kumar, Associate Professor of Mechanical Engineering, Canara Engineering College, Bantwal. So the contents for this lecture are introduction, then limitations of first law, thermal energy reservoirs and heat engines. So let us introduce the second law first. So let us study some of the common experience of what we have in our daily life. So we experience that a cup of hot coffee left in a cooler room eventually cools off. So this process satisfies the first law of thermodynamics because the energy lost by the coffee is equal to the energy gained by the surrounding air. So cooling off coffee means it is losing its heat and it is gained by air. Now let us consider the reverse process, cold coffee getting hotter in a cooler room as a result of heat transfer from the room air. So we all know that this process never takes place. So a hot coffee can be cooled by placing it in a room, whereas a cold coffee can never be heated by placing it in a cooler room. So at doing so, we would not violate the first law as long as the amount of energy lost by the air is equal to the amount of energy gained by the coffee. Suppose if this process would have been possible, that means a cold coffee, cup of cold coffee getting heated in a cooler room by absorbing heat from the atmosphere, so it doesn't violate the first law. Because first law says whatever the heat absorbed by one's body or substance should be equal to the heat lost by the another substance or the body. So it doesn't violate the first law. Okay. Okay, now let us consider this example. So you are taking a gas in a closed container as a system, and a paddle wheel is made to rotate inside the system or the gas. Okay, so the rotation of the paddle wheel is done by the lowering of the weight. So in the example, a system undergoes a cycle in which work is first done on the system by the paddle wheel as the weight is lowered. So you have to bring this weight downwards, right? So then paddle wheel, the shaft rotates, so paddle wheel also rotates. So you are transferring work into the system. Now this is negative work because work is done on the system as the weight is lowered. Now to complete the cycle, what we do is we remove now whatever the work energy transferred into the system results in increase in temperature of the system. So now we remove that heat because of this work done on the system, its temperature will increase. Now to bring back it to the initial state or to complete the cycle, we have to transfer the heat to the surroundings. Transfer heat to the surroundings. So it means you have to remove the heat. Now this completes the cycle. Now from experience we know that the process cannot be reversed. So what do you mean by reversing the process? So just now you removed the heat from the system, that is minus Q, to bring the system back to its initial state or to complete the cycle. Now suppose if you supply the same amount of heat, you see as shown by the dotted line, into the system or the gas, so temperature of the gas will increase but the paddle wheel will not turn. You see what happened is when you lowered the weight, negative work is done on the system, okay, minus W is done, and the temperature has increased, and you brought the system back to its initial state by removing the heat. So work transfer is negative and heat transfer is negative, and we are able to bring the system back to its initial state. Now here when the heat is applied to the system, the weight is not raised. That means the system we are not able to convert into work. So this shows that when both heat and work are negative, you can complete the cycle, but when both are positive, so that is not possible, though it is not violating the first law. Now let us consider this example. So all of you know that the heat energy will always flow from a region of high temperature to a region of low temperature. Suppose if we just connect by through a conducting material, right? So heat can easily flow from the region of high temperature to the region of low temperature. But the question is the reverse process possible? So that means transferring heat from the low temperature to the high temperature. As all of you know, this alone does not take place. That means you cannot reverse the process. Okay, so there is explanation here. So system 1 at high temperature, 1 at low temperature. So heat can be transferred from high temperature to the low temperature system. Okay, so this always takes place. But the reverse process, that is transferring heat from the low temperature system to the high temperature system, does not occur, as this is impossible to complete the cycle by heat transfer only. So if there some other like work transfer is involved, so then maybe you are able to complete that. We'll discuss in the later stage. So these two examples led us to the consideration of the heat engine and the heat pump or the refrigerator. So that will be the main topic of our study in this module. Okay, after going through all these examples, now let us discuss or understand the limitations of the first law. Processes proceed in a certain direction and not in the reverse direction. So that is what we studied from all the three examples, that is coffee and then paddle wheel work, as well as the heat transfer from the high temperature to the low temperature system. So they all take place in one direction but not in the reverse direction. The first law places no restriction on the direction of the process. So even if it is reversed, so it doesn't violate the first law, right? But satisfying the first law doesn't ensure that the process will actually occur. So it doesn't violate the first law, but the process is not taking place. That means that if you just satisfy the first law, so you cannot conclude that the process is taking place. It's a very, very important point to be noted. So this inadequacy is overcome by the second law of thermodynamics. So the restriction for a process to actually occur, so that is overcome by the second law of thermodynamics. So a process will not occur unless it satisfies both the first law and the second law of thermodynamics. The use of second law of thermodynamics is not limited to identifying the direction of process. The second law also asserts that energy has quality as well as the quantity. So far the first law, so it only deals with the quantity of the energy, whereas the second law it doesn't not only it identifies the direction of the process, but also it gives idea about the quality of the energy being used. The first law is concerned with the quantity of energy and the transformation of energy from one form to the another with no regard to its quality. So that's what I mentioned just now. The second law provides the necessary means, the quality as well as the degree of degradation of energy during a process. So both the quality as well as the degradation of energy is explained by the second law of thermodynamics. Thus more of high temperature energy can be converted to work, thus it has higher quality than the same amount of energy at lower temperature. So this is a very, very important point to be noted here. If you have the high temperature energy source, right, so it can be converted to work with high quality than the same amount of energy being taken from the low temperature. So that will come across the terms reservoirs. So that we will discuss in the next coming slides. Okay. Now we will discuss what is the meaning of thermal energy reservoir, because this is an important aspect to be understood to study the second law of thermodynamics. So it is an hypothetical body with a relatively large thermal energy capacity. So thermal energy capacity means that it's a product of mass into specific heat, wherein if finite amount of heat is supplied or absorbed from the body, so its temperature will not change. So without undergoing any change in temperature. So a body which doesn't undergo any change in temperature, when finite amount of heat is supplied or removed from the body, so then it is called as the thermal energy reservoir, or sometimes simply we call it as reservoir. So few examples I can give it as atmospheric air. Suppose if you remove any amount of heat or supply some amount of heat to atmospheric air, so there is no change in temperature. Similarly, ocean, lake, rivers. Suppose if you remove or take out some water, or if you add some water, so you cannot find any change in the level of water, right? So even in the ground, okay. So all these things are considered as the energy reservoirs, okay. A reservoir that supplies energy in the form of heat is called as a source. So now this is a very important word. So here onwards you will come across this word many times. And that one absorbs energy in the form of heat is called as a sink. So the one which supplies the energy is called as a source, and the one which absorbs energy is called as a sink. So thermal energy reservoirs are generally referred to as heat reservoirs, since they supply or absorb energy in the form of heat. Okay, so here thermal energy reservoirs. So what examples here I gave are the media in the environment which can be used as the reservoir. So like atmospheric air, ocean, lake, river, right? So if you add some heat to ocean, lake or river, or if you remove some heat, so temperature will not change. Like you remove some quantity of water from itself, or add some water, same way, okay. Similarly the ground, okay. Now let us understand the heat engines. So we know that work can easily be converted into other forms of energy, but converting other forms of energy to work is not that easy. So the mechanical work done by a shaft is converted into internal energy of water in a paddle work. So that is what we have seen. Suppose if you do some shaft work on a water in a container, so this work is transferred into internal energy of water, so that it increases the temperature of water. So this increases the heat of water. So heat content of the water increases. So you are doing some work on the system, taken water as a system, but its temperature is increasing. So work is converted into heat. But the reverse process, that is transferring heat to water, will not cause the shaft to rotate. So that is what we studied under the limitations of the first law. Thus it is clear that work can be converted into heat directly and completely, but converting heat to work requires the use of some special devices. So that is what he meant to say. It is not that easy. So we never said that it is not possible. We said it is not easy. So, but it is easy when you use some special devices. So these devices which convert heat to work are called as the heat engines. So the devices which converts heat energy into mechanical energy or heat energy into work energy, so they are called as the heat engines. The heat engines have the following characteristics. So they receive heat from the high temperature source. They convert part of this heat into work. They reject the remaining waste heat into lower temperature reservoir or sink. Then also they operate in a cycle. So these are the very important characteristics of a heat engine. So it should have a high temperature source or the reservoir from where it absorbs heat, and it converts only part of that heat into work, and the remaining heat is rejected into the low temperature sink, and also the entire heat engine device operates on a cycle, okay. Now this is the pictorial representation of a heat engine. As I told you in the previous slide, so it should have a high temperature source from where so it absorbs heat, or it receives heat rather, right, and converts a part of that heat into work. So that is what it is, the total heat is. It is like like shown like a path wherein small part is moving out as the work, and the remaining part it is rejected to the low temperature sink. So it's a device. You see this device, you see it's shown as heat engine here. So this device, so internally there may be many parts which makes this heat engine, but it absorbs heat from the high temperature source, converts part of that into work, and rejects the remaining into sink, and it works in a cycle. So here we have one more example for that, that is the steam power plant. So here you see the shaded region. So this you can consider as a heat engine. Okay, and it consists of four components as I told in the previous slide. Here it is boiler, turbine, condenser and the pump. So entire this unit taken as the heat engine, so it absorbs heat from the energy source or the high temperature reservoir, and that heat, okay, we already discussed about this, how the boiler absorbs heat and it converts water into steam, and this steam, when it undergoes expansion process in the turbine, so part of that is converted into work. Now remaining steam with a bit of energy content is made to pass through the condenser, where it is made to reject this heat to the atmosphere, which is called as the sink or low temperature reservoir, and then the condensate is fed back to the boiler. So once again, if you take this whole system unit as a heat engine, so it interacts with the two reservoirs. One is at high temperature reservoir, that is energy source, and one at low temperature, which is called as energy sink. It absorbs heat from the high energy source and rejects the heat to the low energy sink, low temperature, that is energy sink, and then part of this heat energy is converted into work. So with this I conclude the lecture 1 of this second law of thermodynamics, and will continue with the lecture number 2. Thank you.